When we evaluate other planets, we often fall into geographic chauvinism, judging their habitability solely by Earth's standards. We look for liquid water, mild temperatures, and familiar atmospheric pressure, forgetting that nature has countless alternative ways to build complex systems. Sometimes, the harshest and most alien worlds turn out to be surprisingly hospitable in some ways, and utterly deadly in others. Titan offers a striking example. Its surface pressure is only about 1.5 times that of Earth, and its thick atmosphere shields it well from deadly cosmic radiation. But beneath that orange sky, temperatures plunge to a bone-chilling minus 180 degrees Celsius. Instead of water, a cycle of liquid methane drives its chemistry. How does this strange world blend conditions that seem almost hospitable to the human body with a chemistry so extreme it turns water into solid rock? And what lies behind this deceptive resemblance to Earth? To understand this, we need to go back to the very beginning. The year is 1655. Dutch astronomer Christian Huygens points his telescope at Saturn and spots a tiny speck nearby. A new moon. Just one of many, it seems. But here's the fascinating part. 3 centuries later, when astronomers managed to measure this speck, they discovered its diameter stretches about 5,150 kilometers. To put that in perspective, that's larger than the entire planet Mercury, a moon bigger than a planet. If Titan orbited the Sun instead of Saturn, it would be classified without question as a full-fledged world of its own. And yet, this world has an atmosphere, not just faint traces of gas or a thin hint of a shell like most moons. A full, dense, heavy atmosphere, with surface pressure that would make a person feel like they're at the bottom of a shallow pool. Familiar, almost cozy. By comparison, Mars has pressure 160 times lower than Earth's. There, blood would boil in seconds without a spacesuit. But on Titan, the pressure is 1.5 times that of Earth's atmosphere, as if someone carefully tuned the conditions just right. But here's what that atmosphere does to every attempt to peer inside. When astronomers first realized in the 20th century that Titan was wrapped in a thick gas envelope, they immediately tried to glimpse its surface. And they saw nothing. Literally nothing. A dense orange haze, a photochemical smog, shrouded the moon in a veil impenetrable to any optical instrument. No telescope, no spectrograph could break through this barrier. A whole world, larger than Mercury, with comfortable pressure and its own weather, and yet completely invisible. Like a safe that looks familiar on the outside, but refuses to open with any key. And here lies a question that has puzzled planetary scientists for decades. What hides beneath that opaque veil? Oceans? Mountains? Empty space? At minus 180 degrees, ordinary water turns into a mineral harder than granite, and the pressure, which might feel familiar, transforms the surface into conditions unlike anything else in the solar system. This is a place where a person could breathe without a compressor, but would freeze to death in just minutes. To uncover the secrets behind this deceptive atmosphere, we had to send the first robotic explorers there. On November 12, 1980, Voyager 1 sped past Titan at a distance of about 4,000 kilometers. It was moving at roughly 20 kilometers per second. The window for detailed imaging lasted only a few hours, and the spacecraft's cameras revealed nothing. Or rather, they revealed exactly what scientists feared, a continuous reddish haze stretching without a single break, without any hint of surface features. The surface stayed out of sight. But here's the interesting part. While the cameras failed, the spectrometers did not. The Voyager instruments couldn't see through the clouds, but they could break those clouds down, molecule by molecule. And what they discovered in that impenetrable haze was the first real clue. Titan's atmosphere turned out to be nitrogen-based, not carbon dioxide like Venus, not hydrogen like the gas giants, nitrogen, just like Earth. About 98% nitrogen. For comparison, the air we breathe right now contains roughly 78% nitrogen. Titan, a moon nearly 900 million miles from the Sun, turned out to be a chemical cousin of Earth. It's like finding a neatly parked bicycle deep in a remote forest. 1,000 miles from the nearest town. Not impossible, but definitely something that needs explaining. And that wasn't the only surprise. Voyager's data also revealed methane in Titan's atmosphere, and, even more importantly, complex organic molecules known as tholins. These carbon-nitrogen compounds are considered the building blocks of biological chemistry here on Earth. In simple terms, Titan's atmosphere wasn't just sitting there, it was actively brewing something. Solar ultraviolet radiation broke methane apart, and its fragments combined with nitrogen to form increasingly complex molecular chains. It was like a whole photochemical lab operating 10 astronomical units from the sun, without guidance or purpose, just physics doing its thing. Voyager moved on, heading toward the edge of the solar system. Meanwhile, planetary scientists were left with a paradox. Beneath those clouds, something chemically alive was stirring, but what exactly remained a mystery. And that mystery held science in place for 17 years. The year was 1997. From Cape Canaveral, the Cassini-Huygens mission launched, a joint project between NASA and the European Space Agency. The spacecraft weighed nearly 6 tons and was about the size of a small bus, equipped with a 4-meter-wide radar antenna. It took 7 years of travel, 4 gravity assists, 2 from Venus, 1 from Earth, and 1 from Jupiter, all just to get there. Finally, Cassini reached Saturn's orbit and aimed its radar, a device that sees through visible light, right through Titan's orange haze. Think of the radar as a microwave echo sounder. It sends out a pulse. The pulse bounces back from the surface, and by analyzing the reflection, scientists reconstruct the terrain. Clouds are invisible to it. This is what came back. Riverbeds. Winding, branching, with tributaries, just like rivers on Earth. Lakes with irregular shapes and well-defined shorelines. But not just lakes. Seas. Huge dark patches on radar maps. The largest, Kraken Mare, covers an area comparable to the Caspian Sea. 400,000 square kilometers of liquid. Wait, liquid at minus 180 degrees? Yes, but not water. Liquid methane and ethane. What exists on Earth only as gas over a stove burner flows through channels on Titan. It collects in basins, evaporates, and falls as rain. A full hydrological cycle, but with hydrocarbons instead of water. Before the Cassini mission, we could only guess about liquids on Titan's surface. After Cassini, we could measure them. This was the first time in history that stable liquid seas and lakes were found on the surface of another body in the solar system. Not just traces, not just a theoretical possibility, a living, breathing system. But the strangest surprise awaited anyone who tried to imagine standing on Titan's surface and looking up. Every other illustration of Titan online shows the same scene. A person stands on the shore of a methane lake with massive Saturn and its rings hanging over the horizon, the sky black and sprinkled with stars. It looks beautiful, romantic, and almost completely wrong. The sky on Titan isn't black, it's orange. Its thick atmosphere, 1.5 times denser than Earth's, scatters sunlight just like our atmosphere does at sunset. Except on Titan, that sunset never ends. The surface lighting feels like a deep Earth twilight. Not full darkness, not night, but that thick, hazy half-light when street lamps haven't turned on yet, and reading outside is already impossible. An orange dusk that lingers no matter the time of day. And the sun? From Titan's surface, the sun would look like a bright spot, visible, but much smaller than the disk we're used to. Titan orbits 10 times farther from the sun than Earth does. The sunlight there is about 100 times weaker. That's enough to color the atmosphere, but not enough to cast the sharp shadows we're familiar with. What about Saturn's rings? Here, we hit the toughest blow to the postcard image. Seeing the rings from Titan's surface would be extremely difficult. First, Titan's orbit lies nearly in the plane of the rings, so they'd appear edge-on, as a thin line, not a grand disk. But more importantly, that thick orange haze, the very one that blocks telescopes from space, also blocks your view from the surface. Standing on Titan, you wouldn't see the rings, or stars, or even a clear outline of Saturn itself. Just a diffuse orange glow, a small, dim sun, and the silent shore of methane. This world looked like the perfect backdrop for a science fiction poster. But it turned out to be something completely different. Not worse, not duller, just different. A place where rivers flow with liquid gas, where a nitrogen atmosphere breathes, where organic chemistry unfolds on its own, without any guiding design. Yet, familiar landmarks vanish here. No stars to navigate by, no rings to grasp a sense of scale. Only an orange haze and chemistry that keeps surprising us. Still, the presence of liquid channels and organic compounds sparked a theory, one that soon crashed and burned. Minus 179 degrees Celsius. This isn't just a number from a textbook. It's a temperature where the rules we've known since childhood completely break down. Water, the foundation of all life on Earth, the universal solvent that every cell depends on, turns into a material as strong as granite at this cold. Not fragile ice like in your freezer, rock. The boulders scattered across Titan's surface, which look like ordinary stones in photos, are actually water ice, worn smooth by erosion over millions of years. And methane, a gas on Earth that bursts from a stove burner and burns away in a flash, flows here through channels, pools in lakes, evaporates, and falls as rain. Simply put, on Titan, water and methane have swapped roles. Water became stone, gas became ocean. And here, even serious scientists have fallen into a tempting trap. Rivers, lakes, organic molecules in the atmosphere, a climate cycle that resembles Earth's. It seems obvious. If it looks so much like Earth, could life here be similar too? Maybe something familiar swims in those methane rivers? No. Life as we know it, built on water, carbon, and proteins, simply can't exist on Titan's surface. And it's not just one reason, it's a combination. The temperature, a chilling 179 degrees below 0 Fahrenheit, kills any biochemistry that depends on liquid water. Because there isn't a drop of liquid water here, all the water is locked away in a crystal lattice, solid as basalt. Enzymes, those protein molecules that speed up chemical reactions in every living cell, freeze in their tracks at these temperatures. It's like trying to get a clock to run when it's sealed in epoxy. The gears are all there, the spring is set, but nothing moves. But this is where the real mystery begins. In 2010, data from an orbital spacecraft revealed something strange. Hydrogen drifting down from the upper atmosphere vanished right at the surface. It didn't scatter. It didn't escape back into space. It simply disappeared. At the same time, scientists found a shortage of acetylene on the surface, a compound calculations predicted should be abundant. These two gases weren't behaving as models expected. Naturally, speculation arose. What if something is consuming them? What if it's a form of metabolism, not Earth-like, but fundamentally different? This idea didn't come out of nowhere. Years before these observations, astrobiologist Chris McKay and NASA biochemist Heather Smith published a theoretical model. They proposed that a hypothetical organism on Titan could use liquid methane or ethane instead of water as a solvent. Instead of breathing oxygen, such a creature would rely on hydrogen, and instead of glucose, it would process acetylene. The model was elegant. It predicted the exact chemical signature that instruments later detected. But here's the crucial part. Most scientists who examined the same data concluded that the anomalies in hydrogen and acetylene result from non-biological processes, catalytic reactions on mineral surfaces, photochemistry in the upper atmosphere, or gaps in the models themselves. Not life, chemistry. Complex, unusual, poorly understood chemistry, but chemistry nonetheless. Still, simply asking the question changed something forever. Before Titan, the idea of the habitable zone meant one thing: the distance from a star where water stays liquid. After Titan, it became clear this definition isn't a law of nature, it's a mindset. If methane can act as a solvent, if energy can come from hydrogen and acetylene, then the habitable zone isn't just a strip around a star, it's a question we still don't know how to answer. Meanwhile, while theorists debated methane-based biochemistry, something was happening on Titan's surface that didn't need any hypotheses. Something visible and tangible, if only we could reach out and touch it. On January 14, 2005, a remarkable event unfolded. The Huygens probe, a disk about 8 feet across, weighing roughly 775 pounds, detached from the Cassini orbiter. It began its descent into Titan's thick orange haze. This was the first and only soft landing ever achieved on a body beyond Mars in our solar system. The descent took 2 hours and 27 minutes. The parachute opened at about 160 kilometers up, and the probe began its slow plunge through an atmosphere 1.5 times denser than Earth's. Not a single ray of sunlight pierced the nitrogen haze. Below stretched an endless, murky veil the color of burnt sugar. The cameras operated blindly. Instruments recorded temperatures at minus 179 degrees Celsius. Pressure climbed steadily. Somewhere beneath this orange blanket lay the surface. But what kind exactly? A liquid methane ocean? An organic stew? Solid ice? The engineers had designed the Huygens to survive any scenario, even a splashdown in liquid. Then, around 20 kilometers altitude, the fog began to thin. For the first time, the cameras captured a glimpse of what lay below. The first images show dark, winding lines stretching from bright highlands down to shadowy lowlands. Channels. They branch, twist, and merge, just like dried-up riverbeds captured in satellite photos of Earth. Not straight like cracks, not random like faults. Winding, that's the key word. In geology, a winding channel means one thing. It was carved by flowing liquid. Slowly, persistently, season after season. These grooves on Titan's surface weren't just river-like, they were rivers. Or rather, the remnants left behind after they dried up. The probe kept descending, just a few meters left, then the impact. It wasn't a hard landing. Huygens touched down at about 5 meters per second, dipped slightly, then settled. Beneath it wasn't an ocean or a slurry, but a relatively firm surface, a thin crust. Below that, the instruments detected a brief spike in methane vapors, as if the probe had landed on damp sand and squeezed liquid out of it. All around, stones lay scattered, rounded and smooth, some the size of a fist or even larger. They spread across the dark plain like pebbles strewn along a dried-up creek bed somewhere in Arizona. But these boulders were nothing like earthly rocks. They were made of water ice. At minus 179 degrees, water freezes into a substance as hard as granite. It becomes solid stone. Literally, a hard, brittle mineral that can be shaped, shattered, and rolled along by flowing liquid. And something, or rather someone, was doing exactly that. The sharp edges have been worn down, the faces smoothed out. These icy rocks carry the marks of erosion, the same kind left behind by a mountain river dragging pebbles along its bed for thousands of years. In simple terms, on Titan, it rained, rivers flowed, and those rivers ground down stones. Only the rain was liquid methane, and the stones were frozen water. And here, scattered clues finally come together into a complete system. Titan has a full climate cycle, a mirror of Earth's water cycle, but built around a completely different substance. Methane evaporates from the surface. It rises into the atmosphere. Then it condenses into clouds. It falls back down as rain. The rain gathers into streams. Streams merge into rivers. Those rivers carve channels through icy rock, roll boulders along, and carry them downhill to lowlands where the liquid pools. Every stage has been confirmed by separate observations. Every link in the chain recorded by instruments. This isn't theory. It's a functioning meteorological system, operating at temperatures where no known Earth life can survive. The probe operated on the surface for just over an hour before its batteries died and the signal was lost. 72 minutes of direct contact with a world located 1.5 billion kilometers from the sun. But that short window was enough to reveal something remarkable. This was not a lifeless icy ball. This was a planetary machine, breathing, flowing, reshaping its own landscape. And somewhere beyond the horizon, out of the Huygens probe's camera reach, those rivers must have been flowing into something. They flowed into seas, not metaphorical lowlands, not dried-out basins, real, stable bodies of liquid. For the first time in the history of observations beyond Earth, open liquid seas appeared on the surface of another world. The Cassini radar cut through Titan's orange haze and revealed 3 dark patches in the northern hemisphere, smooth as polished glass. Kraken Mare, Ligeia Mare, Punga Mare. 3 hydrocarbon basins filled with liquid methane and ethane, clustered in the north. The largest, Kraken Mare, covers an area bigger than the Caspian Sea. These aren't lakes or puddles. They're full-fledged seas, complete with shorelines, depths, and radar reflections that mirror the glint of sunlight on Earth's oceans. Here's the strange part. All 3 seas lie in the north. Meanwhile, the southern hemisphere remains almost bone dry. On a world with a single active climate cycle, this kind of asymmetry seems like a miscalculation. But it isn't. The answer lies in Saturn's orbit. It takes nearly 30 Earth years for Titan to complete one full trip around the Sun. Each season on Titan lasts over 7 years. 7 years of summer, 7 years of winter. During these stretched-out seasons, methane slowly shifts between the hemispheres, like water in a giant basin that someone tilts ever so slowly from side to side. Right now, in this current era, methane has gathered in the north. In about 15 Earth years, the balance will start to shift. After 30 years, the seas might begin to shrink, while the southern lowlands, now empty, will fill up again. One climate cycle on Titan lasts longer than the entire career of the scientist studying it. What we see is just a single snapshot of a process that unfolds over decades. And here is where the real paradox begins. Titan receives 100 times less energy from the sun than Earth does. 100 times less. Imagine trying to heat an entire apartment with a single candle burning at the far end of a hallway. By any earthly standard, that amount of heat wouldn't be nearly enough for anything. Not evaporation, not convection, not cloud formation. Yet clouds stretch across hundreds of miles above Titan's surface. Methane rains pour down onto frozen ground, carving liquid channels that spread across the plains. These channels leave marks strikingly similar to seasonal floods in Earth's deserts. Storms reshape the landscape, not over millions of years, but within a single season. Titan's weather operates on an energy budget so low that on Earth, it wouldn't even stir a gentle breeze. Simply put, this world shouldn't be this active, but it is. Imagine this. You find yourself standing on Titan's equator, not by the seas, not in river valleys, but on a vast plain stretching between them. The ground beneath your feet isn't ice or rock, it's sand. Soft, dark, fine-grained sand. It rolls out to the horizon in smooth ridges, dune after dune, crest after crest, extending for hundreds of miles. The wind here blows at about 1 meter per second, quieter than a whisper of an earthly breeze. Yet it's enough to shift these particles. From satellite images, Titan's dunes look just like those in the Sahara or Namib deserts. Same shape, same scale, same wind patterns. But this sand, it's not sand. On Earth, dunes are made of quartz, tiny fragments of silicate minerals ground down over millions of years. But on Titan, those grains contain not a single atom of silicon. Titan sand is made of complex organic molecules. Carbon compounds clump together into particles as fine as coffee dust. The question of where they come from doesn't lead to the surface. It points upward, hundreds of kilometers into the upper atmosphere. Remember how Titan's story begins? Nitrogen and methane. 2 simple gases that for decades seemed like a dull, unremarkable mix. But these 2 gases serve as raw materials for a chemical factory that runs non-stop. Far above the surface, between 400 and 1200 kilometers up, the sun's ultraviolet light, just a tiny fraction of the energy that actually reaches Saturn's orbit, breaks nitrogen and methane molecules apart. On top of that, Charged particles from Saturn's magnetic field slam into the upper atmosphere. The broken molecular fragments recombine. They link back together, but in new ways. Ethane, acetylene, propane, hydrogen cyanide. The molecules grow heavier, more complex, and larger. They clump into aerosol particles, the same orange haze that hides the surface from telescopes. Then, slowly, over months and years, these particles drift downward, layer by layer. Every year, millions of tons of organic material fall onto Titan's surface as a quiet, invisible snow. This snow never melts. It keeps building up. The wind picks it up, grinds it into fine dust, and pushes it into ridges. These dunes mark the final stop on a journey that begins high in the stratosphere and ends at the equator. The atmosphere creates it, gravity delivers it, the wind shapes the landscape. Every feature on Titan's surface is a product of its sky. On Earth, the cycle of evaporation, condensation, precipitation, erosion, and transport runs on water and demands an immense flow of solar energy to kickstart. On Mars, this cycle stopped long ago. Venus is trapped in a toxic, suffocating steam bath. But on Titan, with just 1% of Earth's energy budget, the same processes happen side by side. A methane-based hydrological cycle on the surface, and an organic photochemical conveyor running in the atmosphere. Two cycles nested within each other, like gears in a clockwork. One churns out liquid, the other creates solid matter. Together, they shape seas, rivers, dunes, clouds, storms, and shorelines. A complete planetary geography crafted with minimal energy. This is arguably one of the most stunning systems we've discovered beyond Earth, a planetary machine that, at just 1% of its power, manages to produce not just weather, but incredibly complex organic chemistry, and then carefully distributes its results across the surface. But no matter how elegant this outer machinery appears, the most unsettling data from the Cassini mission didn't come from the clouds or the dunes. It came from how Titan's icy shell moved relative to its own core, and what that movement revealed about what might be hidden deep inside. The outer shell was moving, not with the core, but separately from it. Data from the Cassini spacecraft revealed that Titan's icy crust shifts relative to its internal structure. Not by tiny fractions of a millimeter, the movements are large enough to track from orbit. The crust slid, slowly, stubbornly, almost as if it were floating on something. And that raises a question you can't easily ignore. What lies between this crust and the rocky core, if one can move independently of the other? A solid body doesn't behave like that. Ice frozen onto rock doesn't crawl away from the rock beneath it. Imagine an eggshell spinning while the yolk inside stays still. The only explanation? There's egg white between the shell and yolk, a liquid layer that lets one slide over the other. Put simply, beneath Titan's ice shell, tens of kilometers thick, there must be liquid. And this is where the real mystery begins, because the calculations don't reveal a puddle, not a subterranean lake, not a pocket of meltwater trapped in a cavity. According to the models, beneath Titan's icy shell lies a global ocean of liquid water mixed with ammonia. Ammonia acts like antifreeze. It lowers the freezing point, letting the water stay liquid at minus 97 degrees Celsius, where pure ice would have long since frozen solid. Global, not regional, not local. It wraps around the entire moon. And it's the sheer scale of this reservoir that truly blows your mind. Titan's underground ocean could hold many times the volume of all Earth's oceans combined. All of them. The Pacific, Atlantic, Indian, and Arctic Oceans together. Beneath a toxic orange haze, hidden under dunes made of tiny plastic-like grains, and flowing beneath rivers of methane, there's more liquid water here than on our entire planet. While we've searched for water on Mars drop by drop, tracing dried-up riverbeds, Titan hides an entire ocean behind a wall of ice. But even if the ocean exists, it might not be completely isolated. Some surface features on Titan could be cryovolcanoes, volcanoes that erupt not molten rock, but a slurry of water, ammonia, and other materials squeezed up from deep below. Instead of lava, they release icy slush that seeps through cracks and spreads across the frozen plains. If cryovolcanism, this process of cold eruptions, is really at work, it creates a direct link between the ocean and the surface. Material rises up, the chemistry of the interior seeps out. That means we can study the ocean's composition without drilling through a single inch of ice, simply by analyzing what it spits out onto the surface. Why does this matter? Because Titan's subsurface ocean offers a far more promising place to look for life than anything on the surface. There, liquid water flows. There's protection from cosmic radiation, a shield of ice tens of kilometers thick, far better than any lead barrier. And at the boundary where water meets rock, chemical energy could exist, the same kind that powers hydrothermal vents at the bottom of Earth's oceans. Those black smokers, where life thrives in complete darkness without a single photon of sunlight. Titan's surface is toxic, frozen, and drenched in liquid methane. But beneath it, in silence and darkness, lies an ocean that has never glimpsed the sky. Conditions there might be gentler than anywhere else beyond Earth's open surface. And if this world's dense atmosphere can shield life from radiation above, it begs the question, what else might it allow for anyone daring enough to reach those depths? Titan lets us peer into the past, not just metaphorically, literally. Planetary scientists see it as a natural laboratory for prebiotic chemistry, the very processes that, about 4 billion years ago, slowly assembled the building blocks of life from simple molecules on young Earth. A nitrogen atmosphere, organic compounds raining down on the surface, a liquid environment where these compounds can interact. On Earth, all of this has long been erased by tectonic activity, water, and life itself, which reshaped its own cradle. But on Titan, this process is frozen in time by the cold. It's happening right now, just thousands of times slower. In other words, Titan isn't a lifeless museum. It's a living model, operating on the same principles as early Earth, only in slow motion. Here's the strange part. That dense atmosphere we mentioned at the start, about 1.5 times the pressure at Earth's surface, like being at the bottom of a shallow pool, does more than just protect and preserve. It does something else, and it almost sounds absurd. Titan's gravity is only about 14% of Earth's. Imagine your weight dropping from 176 pounds to just 24. Meanwhile, the air is 4.5 times denser than Earth's atmosphere. Wings in that thick air generate lift with barely any effort. So little effort, in fact, that a person with large enough wings could theoretically fly on Titan using only muscle power. No engine, no fuel, just flapping their arms. This isn't science fiction, it's physics, driven by two key factors: low gravity and high pressure. The very same factors that once seemed like exotic numbers on a chart. This unique combination shaped the design of a mission already in development. Dragonfly, a large multi-rotor craft from NASA, will become the first vehicle ever capable of making long-distance flights across the surface of another world. Not just short hops like the Ingenuity helicopter on Mars. Dragonfly will cover full flights spanning tens of kilometers at a time. But its primary mission isn't geology or mapping. Instead, it aims to explore Titan's chemical evolution and hunt for complex organic compounds that could be linked to the origins of life. The craft will search for the very molecular chains that, on Earth, once formed the first proteins and nucleic acids. Now, let's widen the lens. If humans ever decide to settle deep in the outer reaches of the solar system, Titan offers what neither Mars nor the Moon can. Its thick atmosphere provides strong protection against cosmic radiation. On Mars, you'd have to dig underground to shield yourself. On the Moon, you'd need lead-lined bunkers. On Titan, you can simply stand on the surface. The atmosphere acts like a natural shield, and the resources are remarkable. Lakes and seas of liquid hydrocarbons offer ready-made raw materials for chemical industries. Water ice supplies both water and oxygen. All of this lies right on the surface, no need for deep drilling. It's not perfect for life. Minus 179 degrees Fahrenheit, methane rains, and an orange haze instead of a clear sky. But for survival, Titan ranks among the best places beyond Earth. If prebiotic chemistry isn't just a fluke of one planet, but a natural process that kicks off anywhere nitrogen, organic compounds, and liquids come together, then Titan stops being a distant oddity. It becomes proof. Molecules grow more complex inside a lab flask. Amino acids self-assemble in the Miller-Urey experiment. Organic compounds show up in meteorites that have landed on Earth. Complex organic particles called tholins are constantly forming right now in Titan's atmosphere, all on their own. The same process, unfolding at different scales, in different environments, under different temperatures. Chemical complexity isn't Earth's special privilege. It's a property of matter that has time and energy to work with. 4 billion years ago, Earth looked surprisingly familiar. A thick atmosphere with no oxygen. Organic rain falling from the sky. Liquid water pooling on the surface. Then something snapped, and chemistry turned into biology. Titan froze just one step short of that moment. It won't reveal exactly how life began, but it can show us what the world looked like right before it happened. The Dragonfly mission will reach Titan in the mid-2030s. It will fly on 8 rotors, carry a mass spectrometer, and make a series of landings in different locations. The spacecraft is already under construction. The answer is literally on its way. And whatever it turns out to be, it will challenge our understanding. If complex organic molecules aren't there, then Earth got unbelievably lucky. So much so, it's almost hard to believe. But if they do exist, it means the building blocks of life are spread across the solar system far more generously than we ever imagined. A frozen, shadowed world, drenched in methane, lying 1.5 billion miles from the sun. Yet it might be the clearest mirror where our own planet can glimpse its youth.